Welcome to this next lecture on acoustics. Today we are going to derive the Green function for the acoustic wave equation. In fact, specifically this is called the free space Green function. Free space Green function. Now what is a Green function? What is a Green function? We know that in lumped vibrations, if we have, let us say, mx double dot plus kx is equal to delta of t, where this is a Dirac Delta function. Okay. So that means an impulse is given, impulse like a hammer hit is given. Then the response or the impulse response often denoted by h of t, okay, is such that if any other function, any other excitation is given to the spring mass system, then the response is integral of h of tau f of t minus tau d tau. Okay. So if delta of t is the impulse, h of t is the impulse response. And what is the use of the impulse response? If the system is subjected to f of t and the response is integral 0 to t h of tau f of t minus tau d tau, or the other way also, f of tau h of t minus tau d tau. Okay. So that is what is a impulse input and an impulse response. Okay. Now Green function is the response to an impulse. But here the impulse is in space. Okay. You can have a spatial impulse along with a temporal impulse. Okay. But for our case in this course, our time dependence is always harmonic. Time dependence is harmonic. And so the spatial dependence, spatial impulse is denoted by delta of r or r minus r0 along with the harmonic time dependence. So if in a general coordinate system, if we write the acoustic wave equation, which is like del square P minus 1 over C square del 2 P by del T square is equal to minus a source term, okay. We will call it del Q del T. So now here instead of minus del Q del T, we are going to put a minus delta R minus R0 e to the power of j omega t. Okay. Now since the time dependence is harmonic, on this side what we will get is okay, this side we get a G, which is the free space Green function. Okay. So if we cancel the temporal terms, del square G R comma R0 plus K square G R comma R0 is equal to minus delta R minus R0. Okay. So the G is the free space Green function, and it always has these two variables, the function of these two variables. Okay. R is where the response is measured, response point, response location or measurement location, and R0 is where the impulse is given. Impulse location, source location. Okay. Now this is called the free space Green function because there is no other source, in the medium, till infinity. Or no boundary condition, no boundary till infinity. Hence free space. Okay. So this is the only source located at R equal to R0, which is harmonic and it sits in an infinite medium. Okay. So the Green function G satisfies del square plus K square G R comma R0 is equal to 0 everywhere. Except at R equal to R0. So the G satisfies the homogeneous Helmholtz equation. Okay. So the homogeneous Helmholtz equation. Everywhere except at R equal to R0, and at R equal to R0 we have del square plus K square G of R comma R0 equal to minus delta R minus R0. Okay. This negative, if you recall, comes from the when we derived the acoustic wave equation with a source, with a volume source. volume velocity source. That's where the minus comes from. Okay. So now this delta, okay, this delta as a property, let us say in Cartesian, in rectangular Cartesian, coordinate, this delta of r minus r0 looks like delta of x minus x0, delta of y minus y0, delta of z minus z0. Okay. So, there are three delta functions, so that it has the unit of 1 over L cube. Okay. So, now in spherical coordinates, this delta looks like one over r square sine theta delta of r minus r0 theta minus theta 0 delta of phi minus phi 0. Okay. Why is that? Because if I do this delta integral in Cartesian coordinates over a volume which includes the delta, where the delta is applied, this volume is over a region, delta is applied, and I am integrating over a small volume also, but that volume includes the location of the delta, then I get a 1. Similarly, for spherical coordinates, if I integrate over a volume, let us say 0 to a, 0 to twice pi for the azimuthal coordinate, and 0 to pi for the elevation coordinate polar angle, and I have 1 over r square sine theta delta of. So, this r is actually you can say a vector, or okay, it points to a location in r theta phi coordinate, whereas this is just the radial coordinate. Okay, please mind that. I will come back to this notation. So, okay, so I have delta just the r coordinate, delta theta coordinate, delta phi coordinate, and I am doing it in spherical. So, I need this elemental volume r square sine theta d theta d phi dr. Okay. This is the volume element in spherical coordinates. So, now this cancels with that, and if I integrate now, I get a 1. Okay. So, that is how a 3D delta looks like in spherical coordinates. Now, so what I have here is I will go to spherical coordinates. I will go to spherical coordinates with theta phi symmetry. Theta phi symmetry. Okay, and the particular del square with theta phi symmetry looks like del 2 by del r square plus 2 by r del r plus k square, let us say p is equal to 0. The theta phi terms are not there because it has theta and phi symmetry. Okay. Now we will do something else. Suppose I had del 2 del r square of r times p plus k square of r times p equal to 0. Okay. Then what would this be? Let us open this out and see what happens. So I have del by del r of del by del r of rp r times p plus k square into r times p is a 0. So derivative of r is 1, so I get a p plus r del p by del r. I have one more del del r plus k square rp. So I get del p by del r plus del p by del r plus r del 2p by del r square plus k square into r into p equal to 0. Okay. So if I divide this by r, I get del 2 del r square plus 2 r del del r plus k square of p equal to 0. So this is the same equation as that. Okay. Theta phi is symmetric spherical equation. So this ends up as this operator on. Okay. If I expand it, it looks like this. But if I still stick with this del 2 by del r square rp plus k square of rp equal to 0. Okay, so how does it look like? It looks like to me del 2 by del x square plus k square of p equal to 0. Then what is it? Then p of x I can write as a, let's say tilde e to the power of minus jkx plus b tilde e to the power of jkx, right. So in this case what do I do? In this case now I can write rp is equal to a tilde e to the power of minus jkr plus b tilde e to the power of jkr. Okay. Just by similarity logic, this has this solution del del x square plus k square, here del del r square plus k square. So rp will have the same solution. So now p looks like a tilde by r minus jkr plus b tilde by r e to the power jkr. Okay. So that's the solution to this homogeneous form. Okay. Now if I take this and I replace this with a g, I replace it with a g, okay. Now, or let me just replace it with a g of r. Okay. Then what will g of r look like? It will look like p of r a tilde e to the power of minus jkr over r plus B tilde e to the power plus jkr over r. Okay. So, what did we say? If this is del square for me, if this is del square in symmetric theta phi symmetric spherical coordinate, okay, then I have the inhomogeneous equation is del square plus k square g of r 0 is 0 as minus delta of r, and del square plus k square is g of r, I mean of g of r is 0 for r not equal to 0, okay, satisfies. Okay. So, that means what, where r is not equal to 0, that means where the impulse is not there, the solution is this, I am just repeating, A tilde by r plus B tilde by r by jkr. Now, if I put in the harmonic dependence, I get g of r e to the power of j omega t, that means it is A tilde by r e to the power of j omega t minus k r plus B tilde by r e to the power j omega t plus k r. Okay. So, we know this is a forward or right travelling wave, and this is a wave travelling with decreasing r, left travelling wave. Okay. Now, because we are in a spherically symmetric coordinate system, okay, this first wave will be outgoing, the second wave will be incoming. Okay. Again, because we are in free space, okay, with a single source, the single point source all the way from here to infinity, and there are no boundary conditions imposed, no boundary conditions imposed. There cannot be an incoming wave, no incoming wave is possible. Okay. This is the only source at origin, for this case it is the origin. Okay. Otherwise, we will put minus delta r minus r 0, where r 0 is the location of the spatial impulse. Then the g acquires another index or argument r comma r 0. So, here we have put an impulse at the origin and nowhere else, and there are no boundary conditions. So, no incoming wave is possible, that means no B is possible. So, B tilde has to be equal to 0. Okay. And so, now my what, G of r must be equal to A tilde over r e to the power of minus j k r. Keep the time out for the moment. Okay. So, now this satisfies the homogeneous equation everywhere except r equal to 0. Okay. Now, at r equal to 0 or r equal to 0, we can't straight away put r equal to 0 in this, because it will blow up. Okay. So, what we are going to do is that we will satisfy the singularity or we will remove the singularity using an integral, in an integral sense. In an integral sense. Okay. That means what? In actuality, this equation over here implies a source. Okay, it implies a source or a mass source which is highly localized. Okay. So if the mass was happening over, mass were being injected into the medium over this much volume, then we integrate over this volume, okay, and that will give us the amount of mass coming out of the region. Okay. So we do a volume integral, and that gives me the mass. Okay. Now if the volume is reduced, okay, then obviously my mass will decrease, mass has to decrease. Okay. But what I will do is, with a reduced volume, I will increase the strength of the mass, or strength of the density, mass per unit volume. Okay. I will increase the mass per unit volume of the source, such that when I now integrate over this smaller volume, I still get the same mass. Okay. Now in the limit, if I take this to a smaller region where the mass is being injected, but I keep the mass constant, then the mass per unit volume will go to infinity, or the mass density will go to infinity. Okay. Such that when I integrate this over the small volume, m by volume which has gone to a very high value, I integrate over this small volume, I still manage to get the same mass. Okay. So that is what is the idea over here. With a delta function, there is a infinitesimally small region over this mass is being injected, okay, such that the density, mass per unit volume is very high, okay, such that when I integrate it over this small volume, okay, d volume, I get the same mass out. So now if we leave it out like this, it is a singularity, but if we integrate this out, okay, then in an integral sense we get a finite value which is manageable. Okay, that is the idea of a delta function. Okay. Things are happening over a very small region, but once you integrate around the region, if certain amount of finite quantity is either taken out or injected. Okay, that is the idea. So we will satisfy this equation in an integral sense. Okay. So now what we do here, so my g of r is currently a e to the power of minus j k r over r. Okay. And now I will put it into this equation, del square plus k square, okay, a over r e to the power of minus j k r is equal to minus delta of r. Okay. using this equation and using the properties of delta function in an integral sense, we will have to find the value of A. That is the value unknown. In here A is unknown. The spherical coordinates that entire section of Bessel functions and spherical harmonics, the details and the free space green function derivation, the Kirchhoff-Helmholtz integral equation and green function, the Neumann kind and the Dirichlet kind, interior, exterior, and the examples of spherical piston or spherical cap on a rigid sphere or a point source on a sphere, okay, scattering. All these have been taken from Fourier acoustics by Earl G. Williams. I have mentioned this before. Okay. So that we will do in the next class. Thank you.